Hey guys, so I'm gonna try and go through some of the practice set for chapter 28. With our first one, we have light with a wavelength of 420 nanometers shines on a metal surface, which emits electrons. The stopping potential is measured to be 0.66 volts. What is the maximum speed of the emitted electrons? Spoiler alert, it's that. So let's start with, we have that, it gave us that lambda is equal to 420 nanometers, and our V stop is 0.66 volts. We want to find the velocity. For that, we are going to use K max is equal to E V stop. That is from the chapter, I think page 3. Kinetic energy is, remember, it's the same as it was before. So that's 1/2 mv squared is going to equal E V stop. Rearrange that and we get V squared equals 2 E V stop over m equals 2. E is the charge of an electron. So 2 times 1.6 10 to the minus 19 coulombs. That's one you should know. And it's just the magnitude of that charge. It's not the sign. Times our V stop. Divided by mass. That's another one that you should know. And when you do that all out, do the math, you get velocity to be 4.81 times 10 to the 5 meters per second. Now, we're going to calculate the work function. The work function is the amount of energy that it takes to remove an electron from a piece of metal. The equation that we're going to use is we have K max equals HF minus HF0. So that equals EE minus E0. And remember that F is equal to C over lambda. Frequency is velocity over wavelength. We have our statement for, we have another way of writing out kinetic energy up here. So we're going to write this out in a way that we can plug stuff in. So E V stop equals H C over lambda minus the work function. We're trying to solve for that E0 on its own. We're going to do something kind of, I guess you could say, interesting here. We've been talking about using electron volts versus using joules. what you do is when you have an electron volt, you're literally just saying that voltage times E. That voltage times an electron. So where we say that V stop is equal to 0.66 volts, we have that K is equal to E times V. E times V stop. We're now going to say that K max is equal to 0.66 electron volts. It's got the voltage, that's where we got that from. And we're saying if you take that and multiply it by 1.66 10 to the minus 19, you'll get the kinetic energy. So what we're going to do here is we are going to say that 0.66 electron volts is equal to, we're going to use the other form of Planck's constant, 4.41 times 10 to the minus 15 electron volt seconds. 3 times 10 to the 8, that's C, over 420 times 10 to the minus 9, minus E0. If you do that math out, we get 0.66 EV equals 2.96 EV minus E0 minus the work function. We get the work function to be 2.3 electron volts. To kind of see about, so we've got two versions of H. We've got H equals 6.63 times 10 to the minus 34 joule seconds, and we've also got H equals 4.14 10 to the minus 15 electron volt seconds. What we're actually saying with this, if you take the 6.63 times 10 to the minus 34, multiply that by 1.6 10 to the minus 19 coulombs. So if you take this here and multiply it by E, so if we take HE, we then get H equals 4.14 times 10 to the minus 15. The units do check out. Kind of play with that so that you can see what it's doing. Whenever we have E in front of V, like EV, you can plug in 1.6 10 to the minus 19 and you should get an answer that would be like in joules. That would convert it to joules. This is a newer thing that we're doing. Electron volt takes a little getting used to, but it's very convenient once you start using it. For the next one, what is the wavelength in nanometers of a photon with energy of 0.3 electron volts? For this, the wavelength of a photon with that energy. A photon with that energy, so a photon with that energy is the EE. So when we have K max equals EE minus E0, this EE is the energy given to the electron by the photon. So this EE is the electron energy. So a photon with an energy of that, EE is equal to HF, which is equal to hc over lambda. So we can actually just plug in. If we're using electron volts, we can just plug right in. So 0.3 electron volts equals 4.14 times 10 to the minus 15 electron volt seconds. 310 to the 8 meters per second over lambda. We get a lambda of 4140 nanometers. Whenever the energy that we're talking about is in electron volts, that's when you use the 4.14 for H. If the energy that we're talking about is in joules, then you want to use the 6.63. So match up electron volts with electron volts, match up joules with joules. You want to design a photodetector that can respond to the entire range of the visible spectrum. What is the maximum possible work function of the cathode? We'll start out by saying, I guess this isn't really common knowledge, but we say that the visible spectrum ranges from 400 to 700 nanometers. That's the wavelength that we're working with. We're going to be using the photoelectric effect. Kmax equals EE minus E0. We are going to be looking at the energy given to the electron by the photon. A red photon has the least amount of energy. Red is around the 700 nanometers. So this work function, to get an electron to come off of the metal, a red photon needs to be able to provide the amount of energy to get an electron off the metal. So the work function would have to be equal to that red, what you get with a red wavelength. So we want that work function is going to equal the energy given to the electron from the photon. So we want E0 to equal EE. So let's start by finding out how much energy is given to an electron when it's hit with red light. EE is equal to HF. We're dealing with electrons, so we will deal in electron volts. I think you could actually do either. You could do electron volts or joules, but the numbers are a lot better if you deal with electron volts here. So the H that we're going to use is 4.14 times 10 to the minus 15 electron volt seconds. For frequency, we're actually going to rewrite this equation as H times C over lambda times 310 to the 8 over 700 times 10 to the minus 9. That will say that an electron hit with red light acquires 1.78 electron volts of energy. So that would mean that if we want this photodetector to respond to red light, then it has to respond to energies of 1.78 electron volts. So that has to be our work function.